Thank you, Arnav. A very good morning, ladies and gentlemen. I welcome you to the next session of the Research Scholar Day 2021, the annual Research Festival of IIT Madras. It gives me great pleasure and honor to welcome our speaker of the session, Dr. Arish Pitchai and Abhishek Chopra. Welcome, sir. Abhishek Chopra, founder and chief executive officer, is currently a PhD student at Rice Polytechnic Institute, USA, pursuing aerospace engineering, and his research specialization is developing high fidelity and parallel computational fluid dynamics code for rotorcraft applications. He has several technical publications, including journal and conference paper under his name. At BQP, he focused on the holistic growth of each aspect of the startup, from business, marketing, and technical team. He also leads the quantum computing team at BQP. The second speaker of the day, Dr. Arish Pitchai, the quantum scientist. He is currently a professor at Christ University, Bangalore. He obtained his PhD in quantum computing from the NIT Trichy, India. He worked as an associate consultant and R&D. He's working at R&D at Atos, Pune. His research interests include quantum computing, game theory, artificial intelligence, and algorithm. He has published several research papers in referred international journal and international conference at BQP. He is monitoring the quantum team in research and development. He brings a wealth of knowledge as well as the established in academic industry partnership. I welcome you both, sir, on the board. Over to you, sir.
Hello. Can everyone hear me?
Yes, sir.
Okay, perfect. So let me just share my screen. So first of all, thank you everyone. Thank you for the team IIT Bombay, IIT Madras to welcome us. It's a great pleasure that we are here to represent BosonQ. Quick introduction. Today we are going to talk about some of the aspects of multiphysics simulation, which is part of like BosonQ's main mission. Then we will talk about the need for quantum computing, then some introduction about quantum computing, and then how BosonQ is leveraging the power of quantum computing. We also, at the end of the session, will have some opportunity for the audience to see what's going on in BosonQ and how can they become part of this amazing startup. So before that, let's start with the introduction of speaker. So here, I'll go ahead with my introduction. So we have a four-member founding team. Myself, Abhishek Chopra. I'm the founder and CEO of BosonQ. I'm currently a PhD candidate at Rice Polytechnic Institute, where I'm pursuing aerospace engineering. I develop high-fidelity CPU, GPU-based computational fluid dynamics code with rotorcraft application. Before that, I finished my bachelor's in aerospace engineering at Rutgers University, where I met Ruth and Hassan. Also, this is my academic side of things, but at BosonQ, it has been a great journey so far. We started in September 2020, and we have gained great amount of interest in an idea and the product that we are currently developing. We consider this as a leading Indian startup, which was recently also published by the Analytical magazine. But what goes on behind is something that we work tirelessly day in, day out, and believing in this idea, which is actually quite challenging, and how challenging that will be cleared in furthermore slide. And we are still growing, and we want to be the representation from India at a global stage. So quickly introducing other members. Ruth Lainsola is the CTO. Hassan Azmat is the Chief Business Officer, and then Jash Minocha is the Chief Commercial Officer. Their current academic you can see down below. I would like to ask Dr. Pitchai if you can introduce himself, and then I will introduce the rest of the advisory board and technical leaders.
Thank you, Abhishek, for giving this opportunity. I'm Arish Pitchai. who is interested in quantum computing like before it was commercially famous. So I started my PhD around 7-8 years back, and that this field impressed me very well. And I continued as after finishing my PhD, I started working as a quantum associate consultant in a company in a quantum R&D. Then right now, the spirit of BosonQ side made me stay in them and to guide them through their expedition. Yeah. Thank you, Abhishek.
Thank you, Dr. Pitchai. So yeah, along with Dr. Pitchai, we have Dr. Chenna Kadapa, who's the multiphysics lead. He is currently a professor at University of Bolton in UK. And then we have this amazing experience advisory board, which helps us both like all from technical business, operational and managerial side of things. So recently, um, with likes of Mr. Vijay Sethi, who's the ex-CIO of Hero MotoCorp, joined our board. And then we have Mr. Ashish Khare, who joined us earlier this year, along with Mr. Satish Bondo. Mr. Alex Khan, who is a very well-known person working with many, has worked with many quantum startups before, and is also a part of Harrisburg University in US. Has also recently um, came into BosonQ as Chief Quantum Advisor. Okay, so that being said, now let's go into the exciting stuff, which is basically who we are. So BosonQ is the first mover in this emerging deep tech space of quantum computing, this disruptive technology that is taking a lot of interest. But we are coming from a very different perspective that we are applying this for multiphysics simulation. And in a slide, I will explain what multiphysics simulation is. We are an enterprise level technology. So basically a B2B. We are only targeting those high level engineering companies. So for example, when I talk about multiphysics, people ask where, like you see ANSYS, Altair, and these are like very student level. How does this become a B2B technology? So in that case, think about multiphysics simulation being applied from anywhere, like designing a building, a bridge, to manufacturing a car or an aeroplane, to even going analyzing the blood flow in your body. Everything between that whole realm can be put into multiphysics simulation. So for us, we are looking at those highly engineering companies like car companies, bike companies, aerospace companies, construction, manufacturing companies who utilize this as a tool. And the interesting part that we are bringing on the table, other than quantum computing, is that we are a SaaS based company. So everything to do with us has to be like you just need a good internet, not even a good local machine, which many traditional softwares require. So for those who do not know or have a background, I would like to help them to understand what multiphysics simulation is. So multiphysics simulation, as I mentioned, is an important part of any kind of engineering design or analysis. So for example, let's say I start my own, um, uh, let's say Tesla, and I want to design or manufacture a new electric vehicle car. So first, what I do is basically first I design the outer aerodynamics of the body. For that, I do fluid dynamics simulation. Then the second important thing is safety of passenger. So we do some kind of crash analysis and all that. For that, we need structural mechanics simulations. Then there is the HVAC part inside the car, how the thermal will flow with batteries now, everything. How will this whole thing happen? That's where we do thermal simulation. Then with autonomous and electric vehicle car, signal processing becomes very, very crucial. And that's where we have electromagnetic simulation. Now, the heart of the electric vehicle car, the battery themselves, requires extensive amount of analysis, which is done through electrochemistry. And last but not the least, the user comfort, that they do not hear noise and everything. That is where acoustic simulations come into picture. So now I gave you a high level idea about what multiphysics is. These things can be studied individually or together. Doing it together is a very complex task and requires very thorough analysis but a lot of computational power. But also each of these physics require high accuracy, especially when they are interlinked with each other or even when they are doing individually. So that is where the need of quantum computing will come into picture. So let me take an example. So here what you see on the right hand side, this is basically telling you why we need high accuracy. So first we have the experiments. So this is basically, think about of a jet coming out of a pipe, a very fast paced jet. This is something that you see similar in your combustion process inside like your engine. So in the experiments, as you see, as time evolves, the things go below and below. And then the traditional softwares actually use this center thing, like center tool called as RANS in this case. It's low accuracy. And you can see how far this is apart. It can capture mean things very well, mean quantities, but not the transients. And that is where the right hand side LES, which is the high accuracy simulation, can play a role. So now you can see the difference between low accuracy and high accuracy, and how much high accuracy is close to the real world. And that is where you need highly accurate simulation. Now here in this example, this was actually carried by my PhD group. This was basically a tail of an aircraft where we were trying to understand the flow behind the tail of an aircraft. You see the level of details. This was done using the same tool that is on the rightmost of the right picture, the LES. But this simulation took 3 million parallel processors. So for those who don't understand the supercomputing language, 3 million parallel processors meaning 3 million computers running all together at the same time. But even with that much computational power, it took about 5 to 6 months to finish this simulation. So you can see how humongous this simulations can get. Um, and this is, mind you, this is just one part of an aircraft. If you, let's say, want to do full aircraft simulation or even full car simulation, it takes months and years. And especially for engineering companies, they do not have that kind of time. That is why they resort to something of like this center line thing, like the RANs, what I showed in the right hand side image. So where we come into picture is that we believe that we need more computational power to do more better simulation. But now I will tell you why that is not possible. So multiphysics simulation need a lot of computational power, as I stated in last slide, meaning that it needs more processing power. One way to do that is like getting bigger supercomputers. That's what the world is currently doing. They're moving from petascale to exascale. I have worked in exascale or started to work in exascale machines in my PhD. But this trend cannot continue because by 2030, we will have zeta scale supercomputers that will require immense amount of electricity. That is 80 megawatts for one supercomputer. To put things into perspective, 80 megawatts meaning 4 times the daily electricity consumption of Mumbai. That's immense. We just cannot spend that much amount of electricity to run just one supercomputer. So what's the other solution? The other solution is to pack more transistor in a chip. Yes, that's what Moore's law says. Many people say the Moore's law is broken or it doesn't follow anymore, and I will leave those things to Dr. Pitchai when he describes his stuff. But what I understand is that they have reached atomic scales where the laws of quantum physics have started to apply, meaning that you cannot go with traditional, like you cannot just go like decrease the size of the transistor and hope that everything remains the same once it reaches the atomic scale. So there is definitely an engineering challenge that comes. So this solution won't work. And that is where the solution of quantum computer works. So quantum computers work in an entirely different paradigm. That is why it is a, and the reason why it is said a disruptive technology is because it is much more powerful than classical computer. In an ideal case scenario, it can be 100 million times faster than a classical computer or even a supercomputer. So now I will let Dr. Pitchai continue from here on, and I will be back for the further slide after he explains and gives you guys a bit of background on quantum computing.
Thank you, Abhishek. Thank you for the introduction to multiphysics simulation and the need for quantum computers. So I really feel privileged to explain the power of quantum computer now. Let's go back to the history of computers. Our first computer was it was very small, like this, in a room. Small in the sense, for them it was small, not for us. It's like I used an ironical word here. It was of a size of a room which is 30 cross 50 foot. So it was invented and started being used during the era of 1946 to 1959. The first computer consisted of vacuum tubes. You should imagine that it has around 17,468 vacuum tubes, and it also had 70,000 resistors, and the capacity of the computer is to add numbers. It has 10,000 capacitors, and it can add 5,000 numbers in 1 second. That was the highest speed achieved. But think of a bigger computer in a room which can do just 5,000 number addition in 1 second. That was not enough for us to do computations, because we have many complex scientific problems to be solved, and this speed is not enough for people to solve those problems. So there came a development. So researchers started keep on making computer faster as well as smaller. So then came the invention of transistors. Then transistors became ICs, and ICs now microprocessors. And where is it going to end? We have different generations of computers. We used to call the first generation computers the one which used vacuum tubes. Second generation computers are the one which use transistors, and then ICs, then microprocessors. So what is the end of this? Where is it going to end? So this drastic change in the speed as well as the size of the computers or the chips was observed by Gordon Moore. So every quantum computer talk will be incomplete without mentioning his name. Gordon Moore is co-founder of Intel, and he observed from 1965. He observed that every 2 years, or approximately every 18 months, the number of transistors being uh, put in a chip or fabricated in a chip is getting double. So he was wondering, and he wrote a paper on it, and that became Moore's law, and that worked. That worked till 2020. So nearly it started slowing down. This Moore's law was working from 1965, but recently, at the end of 2020, like, it started slowing down, and people started doubting whether this Moore's law is going to work in the future also. Because when you go down, when you increase the number of transistors to increase the speed, you have to decrease the size. And either you should decrease the size or you should go for layering. In both the technology, the problem is limitation of size, because we want the computer to be as small as possible, because if it is a bigger one, then we will have energy dissipation. Again, achieving the efficiency will be a problem for us. So what happens if the size keep on decreases? Then by 2030 we have to use atoms as our transistors. Will that solve the problem? Answer is no. Even in July 2020, a single atom transistor of size 2 nanometer was tested in Hebrew University, Jerusalem. That was the smallest transistor tested ever. But the problem with atomical size is bigger. Okay, let's see how the efficiency transformed from 1971. This is the first Intel chip with 2250 transistor, which is of size 10 into 10 power minus 6 meter, and the speed is 740 kilohertz. And very recent faster chip or processor is AMD EPIC ROM, which has 39.5 billion transistors each of size 7 into 10 power 9 meter, and the speed is 3.4 gigahertz. In the past 30 years, the speed became 3,500 times faster and the size became 1,000 times smaller. Is it going to happen in future also? What happens in future? If we have to increase the speed and decrease the size parallelly, because performance is inversely proportional to size. So, and shorter the distance, faster will be the travel of. Information processing is nothing but transfer of bits inside the processor. So shorter the distance will improve the efficiency. So putting a lot of transistors and making the system bigger will not increase the efficiency. So we have to reduce the size of the transistor to increase the efficiency. But the problem is energy dissipation. At one point, the system will not behave as expected. So if you keep on reducing the size, what happens is you have to reach atomic or subatomic level where computers will not behave as expected. Subatomic level is not governed by Newton's law. So the computers cannot become smaller anymore, and atom follows quantum mechanics. This gave birth to the quantum computing era. Now we are in quantum computing era. Like I was waiting for this era for a long time. Since my PhD, I was like, when I started my PhD, people used to give pessimistic statement. They used to say that this is not going to come. This is not going to be a future. But people like us, like-minded people who are interested in quantum computing, survived, and we are seeing the quantum era. We are really happy to see the quantum era. The quantum era is necessary because the speed we achieved in the last 30 years using classical computer is not going to happen in another 30 years. In the next 30 years, we predicted that it is possible to achieve only 50-fold increase in speed using classical computer. So we need an alternative. And Moore's law is almost dead. And we need an alternative. That alternative is nothing but quantum computing. I know most of you heard about this word quantum computing. So I'll take you to the nuts and bolts of it. So that like it will not be a fancy word anymore for you. So quantum computing started like when people started thinking light is a wave. Sorry, I happen to. Earlier, people thought, the physicists thought that light is a wave. Then physicists discovered that, like using Young's double slit experiment and more, they discovered that light also behaves as a particle. Not only light, all the subatomic particles, they have duality property in them. So how to harness this duality property, and what is the counterintuitive effects of duality property? So the world, subatomic particle world, is completely different. It has, because of this duality property, it has two specific or two gifted properties like superposition, and number two is entanglement. The slide is not getting transferred. Okay, yeah, there is a delay in the response. Sorry for this delay. Okay, one is superposition, another is quantum entanglement. Superposition can be thought of being at multiple places in the same time, or if I want to measure a particle, it can have multiple results at the same time. Like before measuring a position of a particle, the position is not determined by a single number. Before measuring a particle, the position cannot be determined by a single number, but with the probability. I'm assuming that some of the audience do not know about physics. Just I want to make it clear for all the audience here. So let me say that if I ask you a question, like if I ask a student, if I let's assume that I'm a professor in IIT Madras and I call the class rep and I ask him, where are you? His answer will be either in college or in hostel or in the cafeteria or in the library. I like IIT Madras library very much. I've been to that library many times. So the answer from the student will be one place. But if I call a subatomic particle and ask, the answer will be like, if you want me to find, you will have probabilities of my position. Like 10 percentage probability of me to be in the classroom, 50 percentage of probability of finding me in the hostel, and 40 percentage of probability or 40 percentage probability of finding me in the cafeteria. So the position of a subatomic particle can be given using probability. Like you will think, how can a person be in multiple places at the same time? Because of the wave particle duality. It spreads its position as a wave, or it specifically speaking, we call it as a probability amplitude. The wave is nothing but probability amplitude. Using the wave function, we can get the probability amplitude. But when I want to see you personally, you will not show the probability and you will stand in front of me. To be more clear, I'll say, like, if I have a electron inside a box, okay, and I'm asking you where inside the box the electron is staying, you cannot give the position of the electron until you take a microscope, an electronic a microscope, to view the electron. When you view the electron, the position collapses, the superposition character property collapses, and it comes down to a single place. But when you don't view the electron, it spreads itself throughout the box. This is what Einstein was worried about. He never supported this quantum computing. So now let's come to quantum entanglement, which is another interesting property of quantum subatomic particles. Entanglement is nothing but when two particles are correlated with each other. When we establish a relationship between two electrons or two subatomic particles, then we take them far apart. A change in one particle will get reflected in another. This is something like you might have experienced in your life. Like suddenly you like this everyone must have experiences. Okay, suddenly one day you will think of a friend to whom you haven't contacted for a long time, and when you think on that day, you will get a call from, maybe after months or after years. This has happened to everyone here, like including me. This is very similar to quantum entanglement. When I make a relationship between two particles and then when I keep them apart, like you can imagine the distance, like one in Earth and another in Mars, still change made in one electron will get reflected in the other. Very recently, using this entanglement, our ISRO showcased free space quantum communication in 300-meter distance. It happened very recently. I guess it is last month or a couple of weeks back. So these are all the special qualities of subatomic particles, which we are going to make use to increase the efficiency of algorithms. So to harness the superposition, there are different mathematicians, and especially the mathematician called Deutsch. He's a physicist, actually. He's an British physicist, and Joshua, an American mathematician. Both of them developed an algorithm called Deutsch-Joshua algorithm, which was capable of solving, which solves a function with multiple values simultaneously. See, in a classical computer, if I want to get f of x for n numbers, I have to do it for n times. N steps will solve the problem. But in a quantum computer, one single query to the quantum computer is capable of giving n answers. It holds the n answers in it. So when you harness the power of entanglement, you have this amazing algorithm called super dense coding. So let's consider that there are two people, Alice and Bob. They want to communicate to each other. They have one of the entangled particle. Each of them have one of them. So like we are making a relationship between the two particles and giving one to Bob and another to Alice. And this super dense coding makes use of the quantum gates, and it finally gives the output. Like if Bob wants to communicate to Alice without any contact, okay, Bob is not going to contact Alice in person. The change made in one particle will get reflected in Alice, and she can read what he is sending. This algorithm is called super dense coding. So these are all some of interesting algorithms. Just I've shown a couple of them. One is solving um, uh, f of x, and another is super dense coding. Give me a second. I'm getting a delay in next slide. Abhishek, I'm experiencing a bit delay in changing the slides. Can you move it for me? Yeah, this is fine now. Abhishek, I'll handle this. If I face any delay, I'll need your assistance to change the slides. Yeah, thank you. So how this happens, how this superposition happens, and how this entanglement happens. Everything starts by taking a subatomic particle. So let me give a very simple example of how a quantum computer makes use of an atom to store values or data and do the processing. Okay, let's take a simple atom which has electrons in it, and everybody knows that the first orbit is called the ground state, and the next one is called the excited state. So in a classical computer, we have on or off. That is, either there will be a voltage inside the flip-flop. Actually, classical computer uses flip-flops or registers. A group of flip-flops is called registers, where when I send a voltage, it is on, and when in the absence of voltage, it is called off. And to make changes in this voltage, we use gates. A similar construct is there in quantum computing. In quantum computing, we used to call ground state as off and excited state as on. When an electron is in ground state, we call it as 0, and when an electron is in excited state, we call it as 1. And we use math, completely linear algebra, to represent everything. Every quantum algorithm is nothing but matrix multiplications. Most of them are matrix multiplications, and we denote every state of an electron using matrices. So this state of electron is denoted with this matrix 1 and 0. Means when I have a 1 in the off position, it means the system is off. When I have a 1 in the on position, which means the system is on. Actually, it is a column vector, but for simplicity and for easy recognition, I have used a row vector. You imagine this is a column vector, and the gate that we are going to use is energy here. When I give energy to this ground state, the electron gets excited, and I will get this answer. When I remove the energy, I can make the electron move from the excited state to ground state. This is how a quantum computer works with information or data. And classically, we have many gates like AND gate, OR gate, XOR gate. This is a very famous gate in classical computer. This is called XOR gate. This is very similar to our two-way switch. This XOR gate will give 1 as an output only when one of the inputs is 1. See, when the input is 0, 0, the output will be 0. When the input is 1, 1, the output will be 0. The input 0, 1 or 1, 0 will give me an output 1. We have a similar classical quantum gate called quantum XOR or CNOT, controlled NOT gate. What it does is it has a control qubit. When the control qubit is 1, the target qubit, we have 2 qubits. Okay, in CNOT gate there will be 2 inputs. Like we have 2 inputs in the classical gate, we have 2 inputs for the quantum CNOT gate. It takes the 2 input, and the target qubit, that is the B, will be changed based on the value of the A, that is the control qubit. This is very, very similar to our classical one. Look at the 0, 0 will give 0, 1, 1 will give 1, 0. The same way it happens in CNOT also. So this shows us that the classical computer can also be mimicked using quantum computer. Quantum computer is not only capable of working on superpositions and entanglements, it is capable of working as a classic. It is an all-rounder. And I would like to introduce an algorithm called Shor's algorithm, which is a very, very famous one, which actually paved way to a new research area called post-quantum cryptography. What Shor's algorithm does is, Shor's algorithm is capable of factoring any number in polynomial time. Factoring a number, an integer, is what important in decrypting or breaking encryptions. So when there is a invention of Shor's algorithm, the cryptographic researchers started thinking like they should start developing classical encryption system which is quantum proof, which is quantum resistant. So this gave rise to a new research field called post-quantum cryptography. And there are very famous simulation platforms available to test these algorithms. And then came our Groover search. This is another famous algorithm which searches an element in a set of unsorted array. So let's imagine if I have 1,000 elements and I have to search a number in that 1,000 numbers. Then the worst case is order of 1,000. I have to pick up all the 1,000 elements. That's the worst case. But Groover search does this in root of n time. This is not an exponential speedup, but still the speedup is very significant. So then came many algorithms which proved the supremacy of quantum computers. And Groover search does it. If you wonder how it does, it just plays with the probability amplitudes of the subatomic particles to get the solution. And now a very famous algorithms in the research, under research and under development and there are some machine learning algorithms which are doing very good job in the field of quantum computing. And people started thinking of combining quantum computer as well as classical computer to get better speed up, and those algorithms are called hybrid quantum algorithms. And this is the present state of present promising state of quantum computers and algorithms. And qubits achieved this, right? Like till now we have seen the algorithm or software point of quantum computing. Now this picture will show you the hardware development in quantum computing. Also, earlier people thought it is very difficult to implement a quantum computer. People used to say that it needs very high engineering, because to make a subatomic particle behave like as you expect, you have to take that subatomic particle to seizing temperature, that is 0 Kelvin. 0 Kelvin is nothing but minus 273 degrees centigrade, which is which needs high cost and high engineering technology. So this made people think pessimistically that achieving a quantum computer physically is not possible. Maybe mathematically you can develop quantum algorithms, but you won't have a machine to implement it. But we have achieved around 1000 qubit by IBM, 5000 qubit by Honeywell, Rigetti, Atos, and many more companies. So I hope I convinced and I made you guys realize that we are going to use quantum computers in near future, and your kids are going to play with quantum computers, and that's our dream. And over to Abhishek now.
Look, can everyone hear me? Okay, so thank you so much, Dr. Pitchai, for that introduction. As Dr. Pitchai said, I hope that we are able to convince people that quantum is the next computing technology. Not and one thing I would like to say that this is something that has not to be thought that it will replace like classical computers. I mean, that is really not possible until next 20 to 30 years. But yes, the most computationally heavy tasks can be performed in quantum computing, which are not possible in classical computing. So moving on with the presentation, this is what my next slide says that if you look at quantum technology, both from the software and the hardware side, we are currently in low TRL region, whereas TRL meaning technology readiness level. But people have started, and especially like these big giants on the right hand side, have started to invest millions and billions of dollars right now. Every country in this world, top like technology country, which includes US, China, uh, France, Germany, Canada, including India, who's investing $1.2 billion in quantum technology for next 5 to 10 years because they see that trend to go down. We need a lot of engineering challenges, both from the hardware and software side. So one such mission BosonQ has taken is that on the software front of things, we are developing our own algorithms. Some of the approaches we have started to take is what Dr. Pitchai showed in part 2 slides back. The hybrid algorithms, the quantum machine algorithms, the quantum inspired algorithms. So we are doing fair bit of research on that. But it is this hybrid, being hybrid is what is the new key right now. It sort of happened with the cars also, that there were purely like diesel petrol engine cars, and then people moved to hybrid cars, and now people are shifting to electric cars. Something similar is what we are doing. We don't want to overwhelm our users with such technology. So the vision that BosonQ brings in is that we want to be the premier multiphysics simulation software company, leveraging the power of quantum computing. And our mission is to make multiphysics simulation a major application area for quantum computing. This is because we see quantum computing in such an interesting field, but the applications are like related to AI, ML, some like optimization problems, but not really multiphysics simulation, which has been the key driver for high performance computing until now. And we are the front runners, and we want to continue being the front runners for multiphysics simulations in quantum computing. So the solution that we are developing currently is a state-of-an-art SaaS-based multiphysics simulation software that is based on hybrid GPU-QPU approach. So multiphysics in general has this community has been a bit behind on computing technology. These most of the softwares and the codes actually run on CPUs and not even GPUs, which is the current trend that is going on. Every hardware provider like Intel, AMD, and all, they produce only GPU. 95% of their supercomputers are GPUs, and 5% computing power is CPU for some task. So that being said, again, we are not a quantum computing company per se. We are a multiphysics simulation software company who's leveraging the power of quantum computing. We have a division on quantum computing. We have people, and in few slides, I'm going to tell about the opportunities that currently exist at BQP in that regime. So that is where we come from. Now, some more exciting part. So the product that actually we are building and bringing to the market, which is still a bit far, is called BQ5. It's a SaaS offering, SaaS being a very major thing. So for a user who wants to access this massive technology of quantum computing that you see, like how quantum computers do, you can actually do that through your laptop itself. We will give you that access. So what you just need is a good internet connection, and then you are a user. If people in the audience they have used multi-physics simulations before, you need CAD, you need meshing and all that. So these are some of the tools that we provide over the cloud, and it's that solver part is what we are redesigning, rethinking, and re-engineering, where we put this hybrid GPU QPU approach, and then once you get that, you have the results. But the important part to note that this whole process is quickened because we are using quantum computer. That's what we are saying or stating. Currently, we have submitted one patent over this thing, and there are multiple patents in the pipeline. But I'm just going to discuss this very briefly. One of the results. So we took the classical approach, the classical algorithm given in the blue line, um, and what we did then was this red line, which was our hybrid classical quantum algorithm. We put it in two different sizes: size problem of 32 and size problem of 64. Um, and what we were able to see that there is a difference. Again, these are theoretical results, but this is what we have observed, that there is a difference in the size 32 problem. The difference is not that much, not that significant. But when you go to a bigger problem size 64, we see that speed up, and that is what we showed as part of our proof of concept. And we say that we can achieve exponential speed up with higher and higher problems. So the bigger the problem size, the much more the speed up is with this hybrid GPU QPU approach. Um, Now we are currently looking towards, so we are a purely software company, and we use hardware from other people who are making these hardware. So IBM, Rigetti, QCI, all come under the architecture that we are currently working for, or working towards, I should say. And the biggest thing that we are keeping in mind is scalability of our technology. That meaning, as Dr. Pitchai was saying, right now we have small qubit system. 2 years from now, we will have bigger, then bigger, and then bigger. So here we have the timeline of IBM. In 2019, they had some qubits, I think so, and then they have plans till 2023 to go above 1,000 qubits. And we say that our technology will be adaptable to this curve. So the more you give the qubit, the better our technology will be able to do, and can adapt to that. So many people will be wondering, how can you introduce quantum computing and not make it complicated? So, well, here is the answer. What you see here is, again, for purpose of this presentation, it's a confidential information, but I'm happy to share here with the audience so that they have a better understanding. Um, Basically, we have this GUI where a multi-physics user comes and does everything. So you can do modeling, setup, mesh simulation, and then see the results. Everything is in the SaaS server. And in the backend is where we have the whole quantum computing going on. So for users, what does it mean? Negligible training cost. So if someone is well versed with multi-physics, they do not need anything else. They can just basically take our software out of the shelf and just start running it because of its nice user-friendly GUI and drag and drop features. So that's about BosonQ size activities on the product side. Um, Many people will be wondering, where are the applications, the real world application this can be applied. So I gave you example of automotive and aerospace, but actually multiphysics is an important tool in biotech, petroleum, renewable energy, astrophysics, and manufacturing. This together makes it a humongous area, a market, which we are trying to cater towards, but only for high accuracy simulation. I showed you the need for high accuracy simulation because you won't perform like surfing web, watching uh, Netflix, or like looking at photos or doing these things do not need quantum computing. Quantum computing are for those tasks which requires a lot of computational power. So even these simulations, which can be very simple, which can be done in few hours, you don't really would like use quantum computing there. You will use quantum computing in bigger problem sizes, which are very much applicable in academia or industry. Anything that takes like week, 1 week at least, or many weeks or many months, and sometimes even many years. That's where this will be applicable. So with that being said, my closing slide. Here at BosonQ, we are currently looking for a senior quantum computing developer. We are also actively looking for quantum computing intern. These openings come and go. And then multi-physics simulation intern with GPU programming in something. For graduate students, we are open to industrial academic collaboration. Like if you're looking for a project, we would be more than happy to talk to. And we are also looking for research collaborations with universities. Currently, BosonQ has gained a lot of traction. We have actually finished three competition, entrepreneur and business pitch competition. We have finished in top one position, like we are the winners of them, and in four of them we have been either runners up or semi-finalists. So we have a lot of interest coming towards our way, and we are very much we belong from academy, as you see the founding team. So we understand and we want to cater towards India, making India Atmanirbhar, in quantum realm. We really want to put India into the map of the world, saying that yes, we can also lead in some technology which is as disruptive as quantum. So that's all we have in the house for everyone today. Please feel free to ask us any questions. You can reach out to us through these means. Uh, we have our website, info@bosonq is a good email to reach out. If you're looking for any job opportunities, check our website. You will have more information there and the kind of projects we are doing. So thank you everyone, and thank you the organizers for having us. I would be happy to take any questions if the audience has.
Okay, thank you, sir. Thank you
Thank
to
you.
Dr. Arish Pitchai and uh, Abhishek Chopra, sir, for such a beautiful and insightful session. As an aeronautical engineer, this session was really fascinating for me, and hope our audience has enjoyed it thoroughly. Thank you for such a beautiful talk again for computational quantum computation. And I will have a question. I will start with myself though. So this, as a CFD person, we really face problem on the mesh size. Okay. So when we increase the mesh size, the computational speed as well as the time it really increase exponentially. So how the quantum computing is going to help with that?
That's a very great question. That's exactly to the heart of what we're doing. So let's say if you currently, let's say you have a simulation you want to do, you use 50 mesh elements, just saying randomly, like a 2D problem, you are doing a CFD, 50 mesh point. You want to go 100. You know that you need more higher accuracy, but you cannot go to that because it takes a lot of time, or your software provider is not giving you that. What BosonQ can do is basically that we can speed these simulations. So the same 50 qubit problem, you can go do 100, make a 100 qubit, sorry, shouldn't say qubit, a 50 mesh size problem can be made a 100 mesh size problem, and then you can use our software and it will give you the same accuracy, but better, uh, better turnaround time, meaning that it will take maybe 2 to 3 times less time if you use our software in that.
So I will request Arnav if they have any question, they have come up with that. And the questions are there in, we are live on YouTube. So there are questions on YouTube, which I will take later.
Yeah, actually, I would like to read out some questions from YouTube comments only. So, yeah, someone has asked, can we do electromagnetic simulation on this platform?
Yeah, we can do electromagnetic. So in my very initial slide, let me just quickly jump on it right now.
Okay, and Another person has asked, how is it different from COMSOL multiphysics software?
Just give me, I will answer those questions very quickly. Just give me one second. Yeah, so here is the answer to the first question. Yes, you can do electromagnetic simulation. So these all are the 6 fields we are starting to put it in our suite of softwares. We are starting with one of them, which is structural mechanics, and then we will go towards other fields. So electromagnetic and electrochemistry will be part of it. Answering the second question, COMSOL. So yes, COMSOL is a traditional software. It works mainly on CPU. The GPU technology is just starting to come up there. They have done trying to do some benchmarking, um, and where they lag is the part of quantum computing, basically. So that is exactly how we are saying. We are not trying to compete or replace these traditional softwares. These traditional software will still be in the place for students, for even for industry when they just want to get a very crude answer to where to look for, basically where to do high fidelity simulation. That's when they will come to us. But in rest of the places, COMSOL, ANSYS, Altair, these companies will be there.
Thank you. We have got another question. How quantum computing is applicable to biotechnology? So if you can specify your applications within.
Sure. So it's a very good question. In biotechnology, there are two, I can tell you from my past experience, two instances, two research that I have personally seen closely. I have not done it myself. Number one is there was this professor back at Rutgers where I did my undergrad. They were looking at blood flow. Um, in the blood flow, they were basically looking at cancer cells and all these. And then further they wanted to make it to a level where CMD can predict those things through simulation, just through simulation, and can do so. Number two is this there was this company called as Heartflow, which was originated from RPI, spun out of RPI, which is where I currently study or do my PhD. They were basically looking at, they made an instrument which had this CFD thing, which used to take pressure near the heart, and then was able to give the results in real world time. Not sure what's happening to them right now. Um, I was in touch with them, but yes, these are the some of the two different applications that can be said. Other applications are definitely like drug delivery, um, disease like Parkinson disease. Someone is trying to do something. So not just in fluid dynamics, but there are structural and thermal and other like electrochemistry. Sometimes acoustic is a very important field which becomes important in biotech. I hope that answers the question.
Yeah.
Thank you, sir, for a great lecture. So, I have a question. Like, you are the one of the frontliners in startup, the context of quantum computing in India. So, how is that ecosystem uh, for you in India?
Great question. Thank you. Someone asked me this question. I was hoping because this platform will really like give me to speak my words. Indian quantum system, to be brutally honest, is very much lagging behind. I have been part of many ecosystems myself. I'm interacting very closely with Canada, with Europe, especially France and Germany. And there was a conference 2 weeks back, QBE, Quantum Business Europe, and I've interacted with not many people. It took them time. It took them like 4 or 5 years to create that ecosystem. That ecosystem currently doesn't exist in India, and we are from that context we are far behind. That is where BosonQ is trying to be not just the leader, like whatever the startup and everything. That's great. I mean, whatever is that, but we really want to push the youth, the experienced people, everyone get that excitedness and like excitement in quantum computing. I saw that with data science, AI, ML that happened 4 or 5 years ago, but really quantum computing is still in its initial stage, and I am very much open along with BosonQ side to support any kind of activities that are going on. Even if people want to go make some startups in quantum computing, go and we are here to support that kind of startups. Mainly like hardware, there's nothing that India is doing. At least we don't know about. Maybe there's something going on the government, but that is sort of the like collaborations where I'm starting to bring the European and the Canadian and the US and the Australian people here in India through courses, through certifications, and these are not to create any much hype for BosonQ. This is to get quantum workforce ready. This is the most important part. Nobody is going to succeed if we don't have the right, intelligent, smart people. And India has abundance of that. Abundance. I cannot tell you how much potential we as a country, we as youth have. It's just where do we put our energy into and how do we put our energy into? So Indian ecosystem needs a lot of input right now. Not just okay, this was one aspect. In terms of investment also, India needs a lot. Just stating that we will give $1.2 billion is not enough. Like that's not enough. You need to pour down, you need to trickle down, you need to give it to startups, you need to give it to people who want to create their startups. So and when this ecosystem develop, the last thing we want to do is compete with each other. Yes, there are friendly competitions that happen here and there, but we as India has to create an ecosystem where one company supports other company, supports the third support. So this whole ecosystem is there. Software, hardware, between software, full stack, all of these are things are possible. And that is the idea I'm gaining from Europe and Canada right now. They're doing a brilliant job there. And I'm asking people to come here, speak to us, create. Like I'm literally asking them to come and create that for India right now. But thank you for bringing that question up. Really appreciate it.
Sir, we have one more question from the audience. How can an electrochemist use this for charge transport for atomic scale devices like memory?
You mean the simulation part? Like how can somebody carry that?
Yeah, most probably that.
Okay,
Charge
I mean,
transport simulation.
yeah. So very simply, all these problems that we think, the one that the person who has a question mentioned, can be converted, has a mathematical basis basically. All these problems, once they become a mathematical basis, you solve it through some different techniques, and in that technique is where what we are basically doing right now with a few of the areas like structural fluids, some part of thermal. You bring us any use case, it always boils down to math. And when it is that math part, that is where we put this hybrid approach for us. And that also being said, hybrid right now, in future we might have pure quantum, but yes, with so-called next era that will be here for 5, 6 years, maybe 7 years. Um, yeah, the hybrid approaches will stand out according to me. So yeah, small answer, yes, that kind of simulation is possible. How is something that you have to look into some paper or something like that. I mean, if I sit down, I can tell you what mathematics is needed there and what software we can use. But yes, once we have our suit possible, that will be possible through BQ5 also.
Thank
Sir,
you.
so one more question I have. Like you told that you will be providing the user software, like say cloud-based one, and you tie up with the IBM and all for the QPU part. So are you going to install your software like directly in the QPU, or again it is connected to the it is connected to the cloud, again it is connected to the user? It's like that.
Um, you're asking the right question. I just didn't understand the last part of it. You mind repeating it or maybe clarifying it
So
a bit?
yeah, so there are like three parts. Like QPU is one part, and your software cloud base is another part, and the user is another part. So is that the structure, or you're directly installing in the in the QPU part your software?
No, QPU part is just being utilized as an accelerator. We are not installing our thing on QPU. We are actually so how SaaS work is basically there is a central system where everything is being stored, and that central part, whenever users give some instruction, and if that needs some kind of simulation, it will access the GPU, the QPU, and whatever. But it is always in that central part. It is stored. So it is basically installed per se in a cloud. the cloud server.
Yes, sir. Thank you.
Thank you, sir, for clearing our doubts. So in IIT Madras, multiple disciplines are working and we are using the CFD phenomenon. So I'll be happy if you share your software details and contacts with our audience.
Sure.
Okay, sir. So with this, I will wrap up this session. Once again, I will ask Arnav to conclude.
Thank you, Abhishek, for that insightful session. It was really application oriented. Like we are from different backgrounds. I'm from mechanical, Nitikesh is from aerospace. So it brings together different phenomena from different backgrounds. And yeah, so the research expo part was also like well accepted by the audience. And thank you for that.
Thank you, sir.
Thank you. Just want to say one thing is that please do not hesitate to reach out to us if you have some ideas, you want to share, you want to do something on your own. We started in similar fashion. We are very young, but one thing that we do differently is basically we do not stop thinking about futuristic ideas. You always have to sow the seed once and for all, and then just believe in your ideas. So, you guys and whoever is watching this, I really give you all the power and the energy that if you have anything that you want to do, do not hesitate to take it up. This is the right time. Never will you find the perfect time. So make the time perfect. So that's all I have for today. Thank you so much for everyone for patiently listening, and thank you
Thank
so
you, sir.
much IIT Madras team for inviting us. It's a pleasure to speak with such a wonderful audience.
Thank you.